Well, I'm very honored to be, both in the organizing committee of this meeting and also, I've been included among the speakers. Well, I was a student in Rome when Bruno Touschek arrived, and immediately after my laureate degree, I attended his courses on quantum field theory, which were really fascinating. And in fact, this conditioned all my future taste in physics, and I was well, and in fact, I became an addicted of quantum field theory, just, I think, because of these lectures by Bruno. And we never worked together, but indirectly, as I will explain, he influenced a lot of my work. Okay, so this is the title. The title is Spontaneous Symmetry Breaking in Particle Physics. No, se no quali testi? Well, the talk I'm going to give is on spontaneous symmetry breaking in particle physics. Actually, the connection with the work of Bruno is somehow indirect. In the history, I will mention the famous attempt of Heisenberg of constructing a nonlinear theory which would describe all the elementary particles, which was partly unsuccessful. But both this theory and a model on which I worked afterwards with Eugenio Nambu, they had an important feature. This was the invariance under a transformation which had been introduced by Bruno and which had been baptized by Heisenberg as the Touschek transformation. So the experience with spontaneous symmetry breaking is very old. Actually, it goes back to the 18th century, and I will divide my talk into four parts, and and I will start just with this prehistory in the 18th century. So it goes back to Euler. Euler discussed the case of a bar, of a thin bar, which was on which a weak force was applied. And for a certain range of the force, of the applied force, this would simply contract according to the Hooke law. However, if the force became sufficiently strong, the bar would start bending. And, and what is interesting that Euler developed also a theory of the critical pressure that you have to exert on the bar. And clearly, once the bar starts bending, Now it lies on a plane, and so you have many equivalent positions in the. So the equilibrium state of the bar is degenerate. And so he gave also a formula, which I believe is essentially correct for the critical load by which the phenomenon of spontaneous breakdown starts. So in the second part of the 50s, Heisenberg made a very ambitious attempt to describe all the particle physics, all the elementary particles, with a unique equation which described the evolution of a spinor. And because you can construct particles of any spin by adding spin 1/2 particles. And this theory was invariant under this equation, this transformation, which is number 3 in this slide. And this equation, this transformation, had been introduced in fact, by Bruno Touschek, and in connection with the Lee and Yang theory of violation of parity. And he introduced the invariance under this transformation to make the neutrino mass exactly equal to 0. And in fact, this is the case if you require so this was the first letter that Bruno wrote on the question of parity conservation and the mass of the neutrino. And so it was very early, it was in the 1st of March 1957, in the letter to the Nuovo Cimento, and the Lee and Yang theory had appeared only a few months before. So Heisenberg probably was the first to mention the possibility of spontaneous symmetry breakdown in particle physics. And however, I mean, he was too ambitious. His theory was not renormalizable, so was not acceptable as a quantum field theory, even if now we understand many more things about non-renormalizability. So the symmetry that he thought it was broken was the isospin invariance. And however, I mean, because it was broken by electromagnetism, but I thought that it could be spontaneously broken. And so in this, in the second part of this slide, that is, I've taken this quotation from his talk at the 1960 Rochester conference. So he says that here we come to a very general mathematical problem, and we should now get accustomed to those problems in which the lowest state is degenerate. There are many different problems in physics that belong to this class. If one develops a new mathematical theory to deal with this class of problems, in the near future, we may make great progress in the theory of elementary particles. And what happened in the decade of the 60s seemed to confirm this, this prediction. So you see the effect of spontaneous breakdown of a symmetry and then the degeneracy of the fundamental state, of the ground state, was well known in condensed matter physics, even if it didn't have a name. I mean, the people in condensed matter physics were so accustomed to this phenomenon that they hadn't given it a name. And the name, in fact, was this name, spontaneous symmetry breaking, appeared only after the transfer of this concept in particle physics. So it's I think the generality of the importance of this phenomenon was in fact appreciated only after the transfer into particle physics. You see, let me take a basic example in which we see in a condensed matter example all the phenomena that then will become important in particle physics. So you see, near the Fermi surface, the electrons and holes when the electron goes above the Fermi surface is described in the famous Barnett-Cooper-Schiffer theory by these two simple equations. And you see the eigenvalues are this square root of epsilon p squared plus phi squared has the same structure of the energy of a relativistic particle. So this quantity phi is called the gap in a superconductor. And so you see it plays the role of a mass because you see the introduction of spontaneous symmetry breaking into particle physics depended very much on an analogy with this. You see, if you, in the Weyl representation, the Dirac equation, you can write it exactly in the same way, and the eigenvalues are just what we know for relativistic particles. So, then in superconductivity, there are excitations which have a zero mass energy spectrum. This was a phenomenon that was discovered by Anderson in his 1958 paper. Then also, I think to a large part independently by Bogolyubov and his school, and then by Rick Eisen, who was a student of Berlin. And then there was a reformulation of the whole theory by Chronodynamics in the 1960s. You see, the idea, the reason why you have problems with these equations is that the eigenstates do not conserve the number of particles. Is in the superconductor do not conserve the charge, which was ensured by the gauge invariance electromagnetism. And so, I mean, they must be accompanied by a backflow which restores the conservation of the charge. This is a concept that was introduced by Feynman in his many papers on the case of helium, superfluid helium. So, I mean, this function, so if you write down an expression of the density, there is a rho zero, which is a density associated with the quasi-particles, so with the states we do not conserve charge. And then there is a function f which describes this backflow. And in fact, the equation which is obeyed by this backflow is, it has an inhomogeneous term, which is just given by the quasi-particles. So in Fourier transform, these equations you see as this structure. So you see that you have a pole at proportional to the momentum squared. And this is, so this is zero mass excitation. However, electrons are charged particles. And so there is, you have to take into account also the Coulomb force, the course. And the Coulomb force actually cancels exactly the singularity of this let's say, zero mass excitation. And actually this pole is shifted to what is called the plasmon, plasma frequency, which is E squared times n is the number of electrons, so is the density of electrons. Now, this fact is very important because once transferred in particle physics is what is called the Higgs mechanism. So superconductivity contains all the ideas that then will become important in particle physics. So this shift of zero mass excitation to the plasma frequency is in fact exactly what will be called later the Higgs phenomenon. There was also another phenomenon in superconductivity, which was the fact that if you apply a magnetic field to a superconductor, this doesn't penetrate except for a small distance into a superconductor. So you see, and then there was a phenomenological theory, which was developed by Landau and Ginzburg, in which you see that actually the electromagnetic field acquires a mass. And so, I mean, all that the phenomena that when later discovered in a relativistic concept are already present in a superconductor. Now, let me, because the model for the transfer of these ideas from time breakdown into particle physics was a model developed by Euclid Nambu and myself. I arrived in Chicago in the fall of 1959, and Nambu was trying to understand this analogy between electromagnetic current and the axial current. Now, the axial current was known not to be conserved exactly. But if you assume that it is conserved exactly, then the most general form that you have for the axial vector constant vertex, which describes the interaction of the beta decay for the axial vector part, is given by this formula. This purely on purely invariance argument. Then you see that you may have a mass term, but you pay a price because you see you have again a pole associated to pseudo-scalar particles of zero mass. So the conservation is compatible with the final nuclear mass m, provided there exists a mass pseudo-scalar meson, which was then called the Nambu-Goldstone particle. Now, at that time, so this is then this was put in a form of a general statement, so abstracting for the particular transformation that we were considering, and this is was called the Goldstone Theorem. So you have the general phenomenon is that these massless bosons appear in the spectrum of the theory, and so you have, for example, the example of ferromagnets. So you have a magnet like those that you put on the refrigerator, and the associated massless boson in that case are spin waves and crystals in which you break the translational invariance, and then you have phonons. So this is the content of what was called at the time the Goldstone Theorem. I remember very well the morning when this paper by Goldstone arrived, and Nambu was very disappointed because he thought that he had the intuition of this phenomenon, and like he was deprived of something. So at the time I arrived in Chicago, Nambu was trying to develop a conjecture. In nature, the axial current is only approximately conserved. Nambu hypothesis was that a small violation of axial current conservation gives a mass to the massless boson, which is then identified with the pi mesons. So under this appointed, he modified the equation that I wrote in the previous slide. Now, this relationship implies a relationship between the pion nucleon coupling constant, the pion decay coupling, and the axial current beta decay constant, GA, and this was known already as the Goldberger-Freeman relation. Now, so when I arrived at Nambu, gave me the text of this letter he was trying to write, and he asked me to check all the calculations and to check also the concepts which were involved, and that is why I was involved. Now, this idea that if you have a small violation of the axial vector conservation, this produces at the same time the mass of the pion and renormalization of the axial vector constant of the beta decay. So we try to make a calculation to see whether this had some foundation, because otherwise the analogy was did not have any meaning. So, we made a calculation on the strict axial vector conservation, assuming that in this case there is no renormalization of the axial vector current. While there was a theorem for the vector part of the beta decay constant, which ensured that there is no renormalization in the case of strict conservation, there was not such a theorem for the axial vector part. So this was just an hypothesis. And then, the relation of conservation gives rise to the fine mass as well as to the ratio of the two constants of beta decay. So we made a calculation, essentially calculating these diagrams in a zero mass pion and finite mass pion and making the subtraction. The calculation involved infinite divergent integrals. And so we did the calculation to be sure in an independent way. Now, and we got different results. So if my result was correct, then we would continue because you see, this was this R is the ratio of these two constants. And we got a very reasonable value. If Yoichiro's result was correct, then we would have abandoned. Finally, I convinced him that my result was correct, and I was very proud of that. And then he decided that you could trust me. So you see that now I have asked some experts some years ago whether with the present knowledge of the standard model, it could be established a relationship as this one, which about the mass of the pion and the renormalization of the axial vector current. But apparently, this is very complicated. So, this calculation actually was under certain hypothesis, but today I think it has no value. But for us was the reason to continue to develop a model of. So the model we developed was again of a Heisenberg type Lagrangian. In Heisenberg theory, there is only the second term, the gamma 5 term. But also this Lagrangian is invariant under the Touschek transformation. And Nambu didn't like very much the Heisenberg theory, but I've been exposed in Rome just due to Bruno Touschek to this theory. In fact, he had invited Heisenberg to give some lectures in Rome about this theory, and I became very enthusiastic. At that time, I believed that one could construct a theory of everything. And but the situation now is much more complicated. And so so that's I mean, I was I liked very much this type of Lagrangian, this nonlinear theory, and I mean, and we cured all the pathologies of a normalizable theory by introducing the cutoff. And we discussed this model in a mean field approximation. And so you have this equation. And then you get a very interesting mass spectrum. You get for the bound states, you get a zero mass pseudoscalar meson, but you get also a bound state of twice the mass of the nucleon, which in fact, I mean, by some authors like Bill Bardeen was taken afterwards as a possible candidate for the Higgs boson. Actually, apparently there is no such boson in the in elementary particles, but this excitation, you see, if you go back to superconductivity, the mass is the place of the mass is taken by the gap, and this excitation twice the gap was found experimentally several years afterwards in superconductivity. So I mean, even if it is, it was. So when I came back to, I mean, I came back to Italy and then went to CERN, and then to discuss in a less rough way the phenomenon of spontaneous breakdown, I introduced this what is became called was called the effective action, and which was a Legendre transform of the generator of vacuum expectation values, and then you can formulate in principle the equation for the vacuum state as a variational principle. And now, the question of the vector mesons. You see, that was became known as the Engler-Braut-Higgs phenomenon. But this was actually anticipated by Philip Anderson in 1963, he, being aware of what was the situation in superconductivity and the fact that the magnetic field acquired a mass, then but the papers by Phil Anderson were very difficult to understand. They were written in a rather cryptic way. So I don't think that everybody could understand what he was saying. But then came simple examples like this one proposed by Engler-Braut. So in which you have the interaction of a vector field with a complex scalar field. And then you can, so you see that if there is a vacuum expectation value of this field, then the vector field acquires a mass, and however, gauge invariance is preserved, because if you calculate the polarization loop first order, then you find that it has this form. So the current is conserved as this. Now, I think that the most important application in particle physics has been the electroreconifigation by Weinberg and Salam. I include this quotation from the paper of Steve Weinberg, and because he proposed the model which was invariant under SU2 times U1 symmetry, and which was spontaneously broken. And he showed that, in fact, the vector mesons transmitting the weak interactions of the beta decay interaction acquire a mass, while the photon remains as with zero mass. And he wrote in particular, we might hope to understand these differences by imagining that the symmetries relating the weak and electromagnetic interactions are exact symmetries of the Lagrangian, but are broken by the vacuum. As far as our model is concerned, it became an effective, what is called an effective field theory for low energy chromodynamics, with the Lagrangian, which contained several terms, so the term of our model, then the Kobayashi-Mascara-2 term, which simulated the axial anomaly, and then since these theories are asymptotically free, the term producing the confinement was treated as perturbation theory, as well as the one particle gluon exchange. So this has been applied in the most different contexts, in nuclear physics and also in particle physics. But I mean, everything, axial vector conservation is not exact, but I mean, in the sense that it's not invariant, chromodynamics is not invariant under the Touschek transformation, but the Touschek is always present in this. Now, can I have 5 minutes? Okay. So, why I want to discuss spontaneous breakdown in a non-equilibrium context? Well, you see, spontaneous symmetry breaking is a phenomenon which takes place very often in statistical mechanics. But it has been studied mainly in equilibrium situations. So, however, it was discovered that by people doing statistical mechanics model, that out of equilibrium, spontaneous breakdown can take place also when it is impossible in equilibrium. And the reason is that you have an additional macroscopic parameter that, and that is, I mean, in a non-equilibrium system, you have always currents flowing through the system. So stationary states are the obvious generalization of equilibrium state, but the condition under which spontaneous symmetry breaking takes place in non-equilibrium are different from equilibrium. So it is worth studying, but it's much more difficult. Let me discuss to see what you meet in non-equilibrium. A toy model, which was proposed some years ago by Popkov, Evans, and David Mukamel. Suppose you have particles which have plus and minus charge. Okay, then you have a bridge, which is the central part of this model, in which, I mean, from one side to the right, the positive particles are injected, and from the left, the negative particles, and so the alpha and beta are the intensities of this. Now you see that this model is CP invariant, because if you change left with right and plus with minus, then you get the same situation. And so then these authors tried to study, at least numerically, the phase diagram of this. You see, I mean, in the central part, which is called the bridge, the two types of particles can exchange their position, as if it were scattering. So, so this is the diagram, and in the B insertion, you see that there is a spontaneous breaking of CP, which is a discrete transformation. So you see the black line is the positive transformation, the positive particles, the density of the positive particles, while the negative particles are very low. And maybe this is done with a finite number of degrees of freedom. Maybe in the limit, just the density of the negative particle goes to zero, while it is maximal density in the entrance, because they get, this is clearly a model also for the traffic jam. And so why I think it's interesting, this phenomenon. I mean, at the cosmic scale, matter is widespread, and we do not see regions with antimatter. And explanations have been proposed invoking initial small fluctuations, which are amplified over a long non-equilibrium evolution to reach the present state. Now, I think this is not very satisfactory to me, because you simply shift to the beginning the problem on the understanding why only one possibility was exploited. So now the universe is not an equilibrium, and then you may try to view baryogenesis as the outcome of a non-equilibrium phase transition. This means that if the non-equilibrium conditions are such that an approximately stationary phase is a spontaneous symmetry breaking phase, and this depends, and depending on the initial condition, the system of interest will relax to one of the degenerate states, avoiding the difficulties of reconstructing the history with many uncertainties. Okay, so now this is the end of my story. And so if you just happens to drive home in a traffic jam and you get stuck, you know that some phase transition has taken place in the traffic, and you may use the time in which you are stuck to think about this problem. And so you may get good ideas for particle physics. Thank you.
If there are no questions online, we can ask if there are here any. No. Okay. Luciano?
I have a comment on your slide 18. the renormalization of GA over GV, which is a very interesting problem.
You said 18?
Yes, it was number 18, if I remember correctly. Now, in this equation, one is, as you say, is the limit of exact symmetry.
See, however, there is no theorem like in the vector case. Yes.
Right. Now, my impression is that the modern version of this is the other Weisberger relation. Because in the other Weisberger relation, you say that the commutator of two axial currents is equal to 1, because it's equal to the vector current, which has matrix element 1 between nucleon. Okay? So you have 1 equal to GA over GV, which is the pole term, which is GA over GV, plus an integral, and the integral is due to the symmetry breaking. And if you do that, you find a very good reproduction of the 1.24.
Oh, I see.
It's the other Weisberger relation, which tells you that, yes, GA over GV is the axial current is a part of a commutator algebra, and 1 is the exact symmetry, but it is broken because there are intermediate states which get into the matrix element of the axial current, connecting the nucleon to the continuum, which is what you try to simulate with one pion exchange.
Yes. But I discussed it with some experts, and one of them was Gino Isidori. And he explained to me that it's very complicated to relate the mass of the pion to see whether these assumptions are reasonable.
Well, my impression is that this is replaced by the other Weisberger relation. Thank you.
Thank you.
I want to start thanking the organizer for this meeting that brought me back to think about this period with a lot of nostalgia and melancholy. And I am very sorry that I could not be in Rome in person. I saw again the Sapienza and Frascati, and I would have very much liked to be there. But unfortunately, I could not come. So I can start with the first transparency. Next one. So I got to know Bruno following his course on statistical mechanics in 1964. And I got immediately fascinated by his way of doing physics, by his very informal personality, and by his free spirit. And in fact, the anecdote that Francis was telling before was one of the reasons why I was very fascinated by Bruno. Then at the beginning of '65, I went to him and I asked if he could give me a thesis. And he was very positive, and he gave me to compute the double Bremsstrahlung, because at that time he was thinking to use it as a monitor for Adone. And in spring '65, I followed his course on QED alla Scuola di Perfezionamento and learn about the Bloch-Nortzig approximation. And I use this approximation to compute the amplitude for very soft photon. Actually, during this year, I was looking back to the Bloch-Nortzig approximation, because now we are using it for emission of graviton. In fact, as this approximation in the '60s was important for Adone, now this approximation may be again important to study the emission of gravitational wave from the black hole merging. And then I started to compute it in QED, and I obtained some partial result that I could then use to get my laurea in February 66. And then I got 1 year fellowship in Frascati and came in contact with Mario Greco, who was performing the same calculation. We joined the force, and after several months, we managed to get a final result. Next transparency. In the meantime, I got a permanent position in Frascati. At the time, was not the INFN, was CNEN. And since it was very painful to compute the double Bremsstrahlung using just 3 diagrams, I didn't have the strength to go into loop calculation like most of the people in the group were doing. And I started to work on finite sum rule as matrix theory, full support with a full support by Bruno. And in '68, I went for 3 months to Caltech, discussing with Frauci on X matrix theory, and follow the lecture by Feynman. If I have time at the end, I will remind you an anecdote with Bruno in this connection. Then in '69, I got a NATO fellowship to go to work in the state. And in '69, I went to MIT to work with Sergio Fubini. I got a leave of absence from Frascati for 1 year, but I wanted to stay a second year. And although I was supported by Bruno and Sergio for this, the director Frascati didn't allow me to stay. And then in 1979, I resigned and I stayed 1 more year at MIT. And then after that, I started my peregrination in Europe, ending up now between Copenhagen at the Niels Bohr Institute and Nordita at Stockholm. Next. Yeah, so usually, if you want to construct an S matrix, you start from the Lagrangian, and then you have a very precise way how to compute the S matrix. But due to the large value of the pion-nucleon coupling constant, in the 60s, a Lagrangian was considered useless for strong interaction. And the idea at that time was to forget Lagrangian, but to try to write directly the S matrix, implementing the axiom of S matrix theory, like closing symmetry, analyticity, unitarity, and Regge behavior. And that should be done using the bootstrap approach that Luciano and Gabriele described already. I will not describe the period that went to allow Gabriele to write the amplitude, because that has been described by Gabriele. I give you just the amplitude, which is the Veneziano model written for 4 scalar particle, which is the amplitude that you see this bit before, and contains a linear rising Regge trajectory, which is this alpha t, which is alpha 0 plus alpha prime s, and has an infinite number of poles whenever alpha t becomes a positive integer. And for S much bigger than t, has Regge behavior, which is given by this formula. Then immediately after Veneziano wrote the amplitude was generalized to n particle, and that model was called dual resonance model. It satisfies all the axioms of S matrix theory with an infinite number of zero-width resonance lying on linearly rising Regge trajectory. Next, please. And so the amplitude was written, and then the question was, is the amplitude consistent? And the other question was, what is the underlying theory? in 69, Fubini, Gordon, and Veneziano rewrote, and also Nambu, rewrote the previous amplitude, introducing an infinite number of harmonic oscillators spaced by integer. And this is the formula. If many of you do not follow this formula, it's not important. The important is that the development at that time started from this formula and try to go from it to the theory, which was the underlying theory of this formula. So it was a bottom-up approach, it was not a top-down approach as you do writing a Lagrangian, when you start from the Lagrangian. So this is the amplitude in terms of the oscillator. And then when you factorize the amplitude at the pole with a mass, which is which is an integer -1 divided by alpha prime, you get the number of states that contribute at the residue, which are given by the next formula. And that formula gives, for instance, at the level n equals 0, you get only the ground state, the tachyon, satisfying this formula. For n equal 1, you get A1 mu, which is a vector meson, a massless vector meson. And for n equal 2, you get A1, and A2, and so on. Next to the formula, you see the Lorentz matrix, which has a minus sign for the zero component. Now, the formula is totally relativistic invariant, and the theory of special relativity requires you to use 4 vectors. But then you see that if you have an odd number of zero component, the state at negative norm, and the negative norm state is a violation of unitarity. It's not consistent with quantum mechanics. And so there must exist some condition that makes some of the states decouple from the physical state. And in fact, Virasoro in 1969 found that for alpha 0 equal 1, there are extra conditions which are called Virasoro conditions that possibly eliminate those ghosts. Next, please. For alpha 0 equal 1, together with the Judice, we found that the on-shell physical state satisfy those conditions. And those conditions, we came to this condition because we learned what happened in thermodynamics in QED, where you have the mu a mu equals 0 condition, that when you go to the quantum theory, it can only be imposed on physical state. And so we got the Ln condition on physical state, which are conditioned in the quantum theory. And Fubini and Veneziano showed that this Virasoro generator satisfies the conformal algebra in 2 dimensions, and Jovais computed using the explicit expression in terms of oscillator, the C number in the Virasoro algebra. Next, please. Then Campagna, Fubini, Napolitano, and Sciuto generalized the amplitude to any physical state. Any physical state is described by Vertex Operator, which is a conformal field with dimension delta equal 1. The lowest one is the tachyon, and the next one is the photon. And the endpoint amplitude can be written exactly like the one with the ground state. And this shows that the model has a democracy. There is a complete democracy among physical states, as suggested by Chu in this book from '66. Next, please. Then the vertex operator for photon was used to compute the D-1 dimensional DDF operator. So remember, the previous operators ran from D dimension. Those ran only on d-2 dimension, which are the dimension orthogonal to the direction of the movement, of the motion of the photon and of the energy of the photon. And these have the important property of commuting with the Ln. So they generate an infinite number of physical state, and they satisfy the algebra of the harmonic oscillator. Unfortunately, at that time, we work in 4 dimensions where these states are not complete, but then later on for 26 dimensions, they become complete. They complete a complete set of states. So next, please. Then already in 69, Nambu, Nielsen, and Susskind suggested the underlying structure of the dual model was a string theory. But in their formulation of the Virasoro algebra, like for instance Nambu did, he wrote a Lagrangian, which was essentially free Lagrangian, and in which the Virasoro algebra appeared as a classification algebra, as now in the conformal field theory, while in the dual resonant model was a gauge algebra which needed to cancel the ghost. And that, for that reason, it took long time to connect what was the dual resonance model to a string theory. And in fact, Nambu and Goto wrote already in 1970 the Nambu-Goto Lagrangian that was a generalization of the particle. As a particle is the word line of the particle. In the string was a wall sheet of the string. And then in front of the Lagrangian, for the point particle, you have a mass, and in front of the string, you have the string tension. But it took a while to understand how to use it. Remember that BRST came only in 74, and also Faddeev-Popov ghost was around that time. So nobody really at that time knew how to quantize the theory, which had a kind of gauge invariance. In addition, the Lagrangian was non-polynomial. You see a square root Lagrangian. And this Lagrangian is completely invariant under any choice of coordinates sigma and tau that you use in the wall sheet. The next, please. Now, a more convenient Lagrangian to use is the one which is just a free scalar theory in 2 dimensions. The 2 dimensions are the tau and sigma. The theory, usually there is a field. Here there is a position of the string, and there is a 2-dimensional metric tensor G. This Lagrangian is classically completely equivalent to the previous one. In fact, if you write the equation of motion for the G mu nu, and you put it back in the Lagrangian, you get an Nambu-Goto action. However, this Lagrangian is much more convenient because the position of the string appears quadratically in the Lagrangian and not in a polynomial way. The fact that the energy momentum tensor is 0 tells you again that the degrees of freedom on the worksheet are non-physical, and because there is a complete invariance under 2-dimensional coordinate transformation. You can choose the conformal gauge, and then in that case, the dependence on G cancel, and you get a free Lagrangian, but with the constraint that you see in the next line. So it's a free Lagrangian with the constraint. The gauge is not yet completely fixed, and we still can perform conformal transformation stay in this gauge, changing just the rho in front of the eta mu nu. But then you can fix completely Lagrangian. You can go into the light-cone gauge, which is given the last formula. And then next transparency, please. And then using the light-cone gauge and the vanishing on energy momentum tensor, you can determine also the x minus in terms of the x orthogonal. And so you see that the only independent component are the d minus 2 transverse direction. And this analysis was performed in the paper by Goddard, Goldstone, Raby, and Thorne. And they check, and they wrote the Lorentz generator substituting the x minus with in terms of the formula in terms of the x transverse. They check the Lorentz algebra, and they check that the Lorentz algebra is satisfied, but only if alpha 0 equal 1 and delta is 26. So in 26, the DDF operator generates a complete set of physical states that are all positive norm, and that implies that the theory, the bosonic string, is Gauss-free. And then this shows that the theory underlying the dual resonance model for D equal 26 is a string theory described by the Namu-Goto action. Next, please. But even before the connection with string theory, the dual resonance model with an infinite number of resonances was considered a tree diagram of a unitary theory. It was consistent with unitarity because there was no ghost, but the zero width resonance contradicted this formula. In fact, the partial width were different from zero, but the total width was zero. And so in such to implement this formula, then people start to compute one loop and even multi-loop, and Lovelace showed that the non-planar loop had cuts violating unitarity unless you are in 26. And so for D equal 26, actually the cuts become poles, and these poles are the pole of the closed string. So the open string state lie on the open string Regge trajectory, and the closed string state lie on the closed string Regge trajectory. And unitarity requires that open string always include closed string. A closed string requires open string, but we will see only at the non-perturbative level. So in this way, you can see that gauge theory always requires gravity and vice versa. You cannot construct a string theory in which you have only gauge theory or only gravity. Next, please. The model, the bosonic string model was not quite realistic for pion physics. And then Neves and Schwartz, they wrote an point amplitude that was more related to pion, and in fact had a G parity property. Pion at G parity -1, and in this amplitude, the coupling of 3 pions was 0. All the analysis can be done that I described before can be done for this model, and the model has no ghost if alpha 0 equal 1 and if d equal 10. Actually, if alpha 0 is a half, as it's for the real raw Regge trajectory for massless pion, one Lovelace-Shapiro got the Lovelace-Shapiro model, which has the interesting property coming from current algebra, the Adler zero. The amplitude, because of the gamma function in the denominator, the amplitude vanish if I put S and T equals 0. Next, please. Now, last year, we were still not convinced you cannot get a pion amplitude. We tried to get a endpoint generalization of the Lovelace-Shapiro model, and that's what we got. It has all the correct Adler zero for the endpoint amplitude. It reduced for alpha prime with 0 to the nonlinear sigma model, as you expect from low energy QCD, but as a negative North Spade ghost. So it seems really that you cannot write a consistent n-pion amplitude with linearly rising Regge trajectory. Next, please. So this, on the right, you see the Lovelace-Shapiro model, which is has the rho and the sigma at the same level. It's not quite realistic because the omega is not at the same level, the rho. And on the left, you see instead the Neve-Schwarz model in which the rho becomes a massless gauge field. And the particle on the blue lines have G parity plus, the particle on the red line have G parity minus, and the amplitude with a non-number of particle with G minus vanish. Next, please. So in hadron physics, only the pion is massless in the chiral limit, but the consistency in theory that I've discussed up to now do not allow a massless pion, but contains massless boson, massless gauge field in the open string sector and a massless graviton in the closed string sector. And in 73, QCD was formulated, and those interested in hadron physics moved to QCD. And in 74, Scherk and Schwartz proposed to use string theory not for hadrons, but as a theory which consistently unified gauge theory with gravity. I should mention that gauge theory and GR are not put by end, but emerge together as an unavoidable part of the theory. And this is also necessary because the only way that we are able to describe massless spin 1 and spin 2 is only having a gauge theory for spin 1 and GR for spin 2. But in the case of the string, there were not different interactions. There was a single interaction, and it was only the interaction among string. And the only physical parameter was that can be fixed from experiment. It's the string tension, or if you want alpha prime, the slope of the Regge trajectory. Next, please. Also, the string coupling constant that enters in the loop expansion is not a free parameter, but is given by the vacuum expectation value of a particular state, which is called a dilaton. I should also mention that string theory is not in contradiction with field theory. It is just an extension of field theory. Field theory amplitude are recovered if you take the limit of infinite tension or alpha prime equals 0. If you look in the previous diagram and you take alpha prime to 0, you see that all the massive state goes to infinity and you are left only with a massless state. And this is consistent with the fact that the string tension tends to keep the string to become a point, but then since the string rotates, there is a centrifugal force which keeps the string open. But if the string tension goes to infinity, then there is no centrifugal force that can make the string to be open, and then you get a point-like particle. And that's field theory is recovered. And the softness of string theory that was a problem with hadrons becomes a virtue in this case, because that gives a finite theory of gravity unified with gauge field theory. Next, please. But then there was a period between, let's say, after when the people abandoned string and went to QCD, in which very few people work on this model, attracted mostly by the beauty of the model, but knowing that this model was not good for hadrons. Now, Ramon and Neve-Schwartz had constructed a model that has, together with bosonic oscillator and as in bosonic string, also fermionic oscillator. It contains a sector with 10-dimensional fermion and a sector with 10-dimensional boson. The spectrum of the state in the bosonic sector is given by this formula. The lowest state is a tachyon, and the next state is a massless gauge boson. Next, please. So this is again the spectrum of the model, but now you should forget the hadrons that you see in the picture. And then there is a fermion number. So the state on the even on the blue Regge trajectory have fermion number 1, and the other in red have fermion number -1. Next, please. In the fermionic sector, so while in the Navier-Stokes sector, the bosonic sector, you have oscillator with half-integer modes. In the fermionic sector, you have oscillator with integer modes. The lowest state is a massless 10-dimensional fermion. The fermionic zero mode satisfies the Dirac gamma matrix algebra. This means that the ground state is a Dirac particle. As that in the case, you have a fermion number which is given by this formula. Next, please. And in 76, Gliossi-Olive and Scherk truncated the spectrum of the Ramon-Navier-Stokes, keeping only the state which are even under the action of the fermion number operator. And this is called the Geoso projection. So the Geoso projection eliminates the state of the Navier-Stokes state that lies on the half-integer trajectory, and the Ramon sector impose the ground state to be a Weil-Majorana fermion. And this is the first string theory without a tachyon in the spectrum. The two lowest states are a gauge field in the bosonic and the massless Weil-Majorana fermion in the fermionic sector. They have the same number of components, 8 in 10 dimensions. It turns that after the Geoso projection, we get at each level the same number of boson and fermions. So this is the spectrum of open type 1 string theory that is a supersymmetric in 10 dimensions. There is also a supersymmetric closed string sector with gravitons, gravitinos, and other massless states. The next, please. Then in the period between after the Geoso projection until 85, more or less the only people who work in this theory were Green and Schwarz, and they constructed what now is called 2A and 2B string. These are two closed string theory. They have two bosonic sector and two fermionic sector. In one bosonic sector, there is a graviton, a dilaton, and a two-index antisymmetric field, which is called Kalb-Ramon, and also gauge field, which have a higher number of Lorentz index. So this generalization of A mu. And in the fermionic sector, there are gravitinos and dilatino. 2B is a chiral theory, 2A instead is non-chiral theory. Those theories contain potential with more than one index. And before I go on, I want to mention that all the development between, that is 65 and 85, so the early period of string theory, are collected in a book that I edited together with a colleague in Firenze, Andrea Cappelli, Elena Castellani, and Filippo Coleman. And in this book, you find those developed in those years. Next, please. So those theories, I mean, the the type 1 and type 2a and 2b contain potential which generalize A mu, the usual gauge potential. And the A mu is characterized by the fact that it couples to point particle given by the coupling by A mu dx mu. Those fields instead couple to objects which are not point-like, but are p-dimensional objects. So an object which has p+1 index coupled to a potential which has p+1 index coupled to an object which has which are p-dimensional. And in fact, in the low energy string effective action, one can compute solution of the classical equation of motion that couple to the metric, the dilaton, and are charged with respect to the Ramon field, which are this potential with a higher number of Lorentz index. And as the Coulomb potential behaves 1 over r, this potential behaves as r to the d minus 3 minus p. And those states are additional non-perturbative states of string theory. And you see that, in fact, the string tension contains the string coupling constant in the denominator. And they are coupled to this higher index potential. In 1894, Polchinski showed that, I mean, there was a symmetry in string theory that was described by Gabriele in his talk. For the closed string, in the closed string, you have a Kaluza-Klein mode, a winding mode, and this symmetry making an exchange between is symmetric under the stage of this mode. In the open string, you have only Kaluza-Klein mode. You cannot have winding mode. The open string cannot wind on the compact direction. And the way to restore T-duality was shown by Polchinski to be that you have to change from Neumann to Dirichlet boundary condition. With Neumann boundary condition, the open string can move in the endpoint of the open string are free to move in the full space. With Dirichlet boundary condition, the two endpoints of the open string are stuck to a certain surface. And these are called Dirichlet branes, and these branes are connected to the classical solution that we saw it before. Next, please. So in the direction orthogonal to the brane, the open string satisfies the Dirichlet boundary condition, and in the direction of the brane, Neumann boundary condition. And so you see that the open string, which contains gauge theory, live on the brane, while gravity connect bottom string can go everywhere in the space. Next, please. If we have a stack of n parallel the brane, then we have n square string, all the open string, and so we have n square open string that is equal to the number of generators of UN gauge group. So the massless bosonic string are gauge field of UN, and the massless fermion states are their supersymmetric particle called gauginos. Next, please. So the gauge theory living on the n maximally supersymmetric D3 brane is the maximal supersymmetric n equal 4 super-Young mills with 1 gluon 6 scalar and 4 Majorana. It is conformally invariant, and Maldacena conjecture that this theory is equivalent to the 10-dimensional string theory in IDS5 cross S5. By now we have a lot of evidence on this, a lot of application of this in hadron physics and condensed matter. However, to have a precise connection to make this connection precise for non-conformal theory as QCD is still to come. And still we have a problem. What is the string theory beyond the Toft large N expansion of QCD as discussed by Gabriele? Next, please. So up to now, we have described the three superstring theory that were constructed before 85. Then two more string came after 85, and this diaterotic with gauge group SO32 and the other with U8 cross U8. And this group, gauge group, are required but to have no gravitational engage anomaly. So those are the 5 superstring theory that are all consistent in 10-dimensional Minkowski space. They are all perturbative inequivalent and supersymmetric in 10 dimensions. Next. But this has generated a puzzle for 10 years. Why string theory is a unique theory, while you have 5 theory instead of just one. And then after 10 years, we understood that there were at the non-perturbative level, they are all connected by a web of weak strong duality. And Witten in 95 show that the 5 string theory are part of a unique 11-dimensional theory called M theory, which is not easy to investigate because there is no explicit formulation. What we know that at low energy it reduced to the 11-dimensional supergravity, and this join the supergravity and the string connection, the string people working on the field, because supergravity always thought that 11 was important, string always thought that 10 was important. Now with M theory, the two communities got together again. Next, please. And this is M theory. And when you compactify M theory in one direction on a circle, then the radius of the 11-dimensional circle is given by GS square root of alpha prime. And this cannot be seen in string perturbation theory. Next, please. The problem is that everything is very beautiful, but the problem is that we observe only 4 and not 10 or 11 dimension. So we are obliged to compactify 6 of these 10 dimension in compact manifold. And if we want n equal 1 supersymmetry, then this manifold must be Calabi-Yau manifold. And then but the low energy physics will depend not only on alpha prime in GS, but also on the size of the manifold and on the moduli, all the closed string field that live in the compact dimension. And these moduli are not fixed in perturbation theory because their potential is completely flat as it happens also for the dilaton. Next, please. So we got a continuum of consistent in equivalent gauge theory, and this is no good from phenomenology. In the last many years, there have been any model for stabilizing this model with flux, and now we have a discrete but a huge number of this possibility that took us to the landscape problem. So the problem is how do you fix the vacuum we live in? So that string theory is a very beautiful theory, unified gravity and gauge theories. However, how to find the theory we live on the standard model is still a big problem for string theory. And with this, I thank you very much for your attention.
No. Okay, any questions here, Luciano?
Paolo, a very beautiful talk and not easy to to master. But I have a very simple question. I listen and I see many papers which speak about the problem of swampland.
Yes.
Can you tell in this scheme what is the swampland?
Swampland is a place, I mean, you want to have, as far as I understand, because I have not worked on the subject lately, you want to construct a consistent theory of gravity. And string is a consistent theory of gravity. Swampland is a region of the moduli space in which the theory will not be consistent, as far as I know. So this possibility that you have in principle must be disregarded.
So you must not fall into the swampland.
Yes, yes.
Okay.